Hello. In this video, we will begin our discussion of the important but somewhat challenging topic of energy. You have probably heard of energy before. Maybe you've heard of energy as the stuff that gives you the strength to get up and run around. Or maybe you think of energy in terms of commodities like electricity, gasoline, and firewood. In this course, we will focus solely on the energy required to make an object move at different speeds. Energy is a difficult term to define, since it covers so many different things. But broadly speaking, we can say that energy is a number that is associated with the state of an object and its properties. We can also consider the energy of a group of objects. For our purposes, we will be concerned with the energy associated with an object's speed and position. To help make this a bit more concrete, let's consider a type of energy we will deal with a lot: kinetic energy. Kinetic energy is the energy associated with an object's motion as well as its mass. In fact, the formula for kinetic energy goes like this: Ke equals 1/2 times the mass times the speed squared. The unit for energy is a joule, which is given by a kilogram times a meter squared per second squared. If you remember that a newton is a kilogram times a meter per second squared, you can play around a bit and realize that a joule is also a newton times a meter. So, as an example, if I have a mass of 60 kilograms and I run at a speed of 8 meters per second, then we can calculate my kinetic energy. My Ke equals 1/2 times 60 kilograms times 8 meters per second squared, which, if we do the arithmetic, is 1920 joules. Alternatively, I could tell you that my kinetic energy is 1000 joules and my mass is still 60 kilograms. How fast am I moving? Go ahead and work that out. You may have run into a bit of a snag when solving this problem. Is my speed 5.8 meters per second or negative 5.8 meters per second? Well, the thing is, kinetic energy doesn't care about what direction you are running in. It only cares about the speed. So if you are given a velocity vector, you should use the magnitude of that vector in the formula. Now that we have seen one type of energy, let's get back to our discussion of energy in general. We said that energy is a number associated with the state of an object, which includes its speed and position. The most important thing about energy is that it cannot be created or destroyed. We therefore say that energy is conserved. There are different forms of energy that an object might have, such as kinetic energy or maybe heat energy. An object may divide its total energy amongst those two types of energies in a lot of different ways, but the total number will remain the same. An object can also interact with another object and transfer some of its energy to that other object. For instance, in a collision, two objects may transfer energy to each other. Let's actually look at a collision example right now. Imagine a football and a basketball collide midair. They both have a mass of a kilogram. Before the collision, the football has 30 joules of energy, and the basketball has 60 joules of energy. In this case, we will assume that all of this energy can only be stored in each object's kinetic energy. After the collision, the football has 40 joules of energy. How fast is the basketball moving? I encourage you to pause here and see if you can work this one out for yourself. Alright, let's solve this. We want the speed of the basketball after the collision, which we can get from the basketball's kinetic energy. After all, Ke equals 1/2 mv squared, so we just need to solve for v. After doing some algebra, you'll find that v squared equals 2 times Ke divided by the mass. Now, we just take the square root of both sides to get an expression for v. While the answer can be positive or negative, we are looking for the speed, so the negative doesn't mean anything. Therefore, we just take the positive solution. So this is a nice expression. After all, we know the mass. However, we don't know the kinetic energy of the basketball after the collision. So let's go figure that out now. Before the collision, the total kinetic energy amongst both objects was 30 joules plus 60 joules, which equals 90 joules. After collision, the total energy must remain the same. So we can write this equation for after the collision. 90 joules equals the kinetic energy of the football plus the kinetic energy of the basketball. Now we can just solve for the kinetic energy of the basketball. It is 90 joules minus the kinetic energy of the football, which is 40 joules. So the Ke of the basketball is 50 joules. Great. We can now take this 50 and plug it into our equations for the speed. 2 times 50 joules divided by 1 kilogram is 100 meters squared per second squared. The square root of that is 10 meters per second. Yay! We got the speed of the basketball. Of course, we don't know which direction it's going, but this is a good start for solving collisions. And that's it for this video. Thanks for watching.